this presentation, we are going to discuss a software architecture case study called A Fresh View of Compilers, which is nothing but the explanation of the evolution of compiler architecture throughout the timeline of the history. For the introduction part, we all know that the compilers are nothing but the translator between the human readable code and the machine executable instruction, where the high-level languages are converted into binary format, that's machine language, which is zeros and ones. Understanding compiler architecture is essential for developers to optimize software performance and efficiency, as it is essential to know the basics. This presentation explores the evolution of compiler architecture from traditional sequential models to modern canonical structures, which will be discussed later in the presentation. The first ever compiler to be introduced is the traditional compiler model in the 1970s. The traditional compiler model, prevalent in 1970s, viewed compilation as a sequential process resembling a pipeline system, as we can see from the picture. The text entered in the compiler and underwent transformations such as lexical analysis, parsing, semantic analysis, optimization, and code generations. This was a sequential system, unlike the modern compilers. A visualization of this process often depicted it as a series of stages with data flowing from one stage to the next. Although this is the first compiler, there are two notable limitations to be discussed here. Despite its prevalence, the traditional model had limitations, notably in managing data flow and maintaining a shared symbol table. The developers found it very difficult to monitor the data flow throughout the translation, that's compilation, so it was a major disadvantage. The second disadvantage is each pass of the compiler often operated on a separate symbol table, leading to inefficiency in data sharing and manipulation. Next is the intermediate representation of compilers. In the 1970s to 1980s timeline, technological advancement and theoretical development in the late 1970s and 1980s led to a transition toward intermediate representation in compiler design. Intermediate representation, such as attributed parse trees, became central to the compilation process. Slowly the changes started, enabling more efficient data manipulation and optimization. And the modern canonical compilers are the one we are using now. The modern compiler architecture shifts the focus from sequential data flow to the centralized shared representation of the program being compiled. This architecture emphasizes the importance of shared representation, such as parse tree, which serves as a locus of compilation information. Unlike the traditional model, where each path operates independently, the modern canonical compiler defines operation on the shared representation, facilitating more efficient compilation. So we may redefine the compiler architecture here. The redefined compiler architecture redirects attention from the sequence of passes to the central shared representation, which is the main concept or main changes we are seeing throughout the changing compilation architecture. Passes in the compiler architecture now denote control flow, while the stronger connection between passes and the shared representation denote data access and manipulation. This redefined architecture presents the compiler as the repository accommodating various tools that operate on the internal representation rather than the textual form of the program. Comparison to the Blackboard architecture. Drawing parallels between compiler architecture and the Blackboard architecture highlights similarities and differences in information processing. Both architectures feature centralized information, that is, we are discussing about the modern compilers, but the execution order in the compiler is predetermined, unlike the Blackboard architecture, where it is determined by incoming database modifications. Implications and applications of the compilers. The modern compiler architecture has significant implications for software development, enabling more efficient compilations and optimization processes. Various tools such as syntax-directed editors and analysis tools leverage the central shared representation for enhanced functionalities and performance. In conclusion, the evolution of compiler architecture reflects advancement in technology and theoretical understandings, leading to more efficient and adaptable compilation processes. Adapting systems architecture to leverage technological advancements is crucial for optimizing software performance and efficiency, which plays a major role in the tech industries. This presentation has explored the journey from traditional sequential models to modern canonical compiler architecture, highlighting the importance of understanding and adapting to changes technological landscapes. Thank you.